I want to do two things tonight. First, I want to tell you how much I appreciate the fact that I have a fabulous job. I have discovered a secret to life, and that's to get paid for having fun. I love my job. I talk to smart people for a living every week. I talk to scientists from all over the world who tell me the latest in science, things that they've just discovered. Doesn't matter what it is, it's all new. And that's what keeps it fresh for me and why I've been doing the show, Quirks and Quarks, for more than 40 years. In fact, the show itself, we just celebrated our 50th anniversary just this season. And it's really quite remarkable that a science show would last for half a century on the CBC. Our ratings have never gone down. So I want to do that. I'll give you a very short video example of how I have a good time doing what I do. And then secondly, I want to give you a perspective on how astronomy and space science has changed our view of ourselves over time. So sort of a little walk through history of how we've had our heads shaken a little bit, and we still are today. It's not over. There's still more that we don't know than what we do know, and I find that very exciting to do it. So first of all, I want to share with you a very short video of an experience that I had where I got to almost make it to space. I've always wanted to be an astronaut. I watched all the moon landings and all of that stuff. Haven't quite made it yet. Maybe it'll still happen as a tourist. But I did get a chance to fly on a zero-G airplane, which is the kind that they use to train astronauts. So the one that I went on is a commercial one that you can buy a ticket on. It's called zero-G. It's not cheap. And so the advantage of being a journalist is that I get somebody else to pay for it, which is another secret when you want to do things. And what they do is they fly out over the ocean, and they do a series of parabolas, which is the natural curve that anything you throw into the air, a baseball or whatever, it follows a parabolic path. And when you throw something, as soon as it leaves your hand, it's weightless, as long as it's in the air. So they have these big airliners where all the seats have been taken out, except 24 of them at the back. And they take out the overhead bin. So it's just a big tube. The windows are covered, which is good. You don't want to see what the airplane's doing. And it's padded all the way around. So you get into the seat in the back. They do the usual, fasten your seatbelt and do all that. And then it's very strange because you're just inside this hollow tube and you hear the engine start up, but you can't tell what the airplane's doing. And so suddenly the engines get loud and you just get pushed back in your seat, but you can't tell if it's going up, down, or anything because you can't see out. And then when they get out over the ocean, you get out of your seat and you lie on your back because they don't want you to move your head. And then they pull the airplane up into a 45-degree climb, which is huge. I mean, that's halfway to straight up. Just to give you perspective on that, when a regular airliner takes off, like a WestJet or a Air Canada, that's 12 degrees. So we're doing 45 degrees. And the airplane can do that because it's only got 24 people on board. There's no cargo, there's no luggage. They just have enough fuel to do this. So it's able to do that. And then when they go over the top, you get 30 seconds of weightlessness. And because you can't see out, it's just like somebody turns off gravity and you just rise up off the floor and suddenly you're weightless and you float around. But what surprised me and what you'll see in this video is that on the first two parabolas, they didn't go to zero because the pilots are controlling this. They don't take the plane up and stall. They actually control it. And they can reduce the G load on you from 1, which you're feeling now, down. They have a little G meter on the dash of the plane, and they're following that as it goes down. So what you're going to see in the video, the first one is they reduced our weight to 1/3, which is the gravity of Mars, because Mars is smaller than the Earth. So you'll see what it's like to walk like a Martian. On the second one, they brought it down to 1/6, which is the gravity of the moon. And you'll see how light that really is. And then you'll see the chaos of zero-G. So let me see if I can get this video started here.
But it makes much bigger hills and valleys. When an airplane is flying along in a straight line, everyone feels the same force of gravity that they do standing on the ground. That's 1G for gravity. But if the plane flies in a hump pattern, it's like going over the top of the hill. The people inside will feel lighter. And if they feel 1/3 of their weight, that's the gravity of Mars. Hey, this is walking on Mars! Hey, this is Mars gravity. This is incredible. This is how you would walk on Mars. If the plane flies over a steeper hump, the people will feel lighter still. At 1/6 of our weight, we feel like we're walking on the moon.
Whoa, this is the moon! This is the moon! This is moon gravity. It's 1/6. This is what they were feeling on the moon. Wow, it's really light. I feel like I could fly. I wonder if I can do a flip. Whoa! Hey, that was easy.
And if the plane flies a really steep path through the air, we'll feel no weight at all, just like the astronauts in space.
Starting to feel really heavy, getting heavier. So I feel twice our weight now. Okay.
Push over. 0G.
Hey, look at me, I'm floating weightless just like an astronaut. And I'm not even in space. This is incredible. So, watch what happens when I throw this ball. I can do all kinds of things.
Look out there. There we go.
Hi there. How's it going today?
Of course, the pilot is in the plane too, so he feels the same thing. How does he know when he's got it just right?
What I do is I hold a pencil or a pen and I let it go, and then I watch the pen. But officially, I have an accelerometer. What this meter does, right now you can see it reads one Earth gravity. When we have it right, this reads 0, and we have it accurate enough to read to 1/100th of a G, or a gravity.
You can see how crazy that really was. Did you notice how light the moon gravity was? I was really surprised by that. That 1/6 of the G, if you're inside a building, when we go back to the moon and they're talking about building colonies, and you're not wearing your spacesuit, you'll be able to jump upstairs to the second floor. You won't need steps. You could just jump up, and you could jump down because you fall slowly. You fall slowly in lunar gravity. So that was a pretty cool experience to do that. And the 0G, you know, it's amazing. Nobody got sick because it's your entire body that's being lifted up. You're not strapped into a seat like in a car. So your whole body comes up, and there's no sense of up and down. You can go any direction you like. Although I found that when you move head first, it feels like you're rising up. And if you move feet first, it feels like you're falling down, even though there is no difference. And when I was doing that tumbling around there, they were spinning me around. On the third tumble around, I began to feel that I was sitting still and the airplane was actually going around me. So it's very disorienting, but it's beautiful. It's really a lot of fun to do that. So as you can see, I do a lot of fun things in my work, and that's the secret to life, is to have fun. So the title of my presentation tonight, I'm calling, What If Everything We Know Is Wrong? What if everything we know is wrong? And let me just see if I can share my slides here. So what if everything we know is wrong? And the reason I ask this is because we've been wrong many times in the past. We thought that, well, if you only see the world through your 5 senses, through what you can see and look around you, the Earth looks flat. It really does look flat. The sky looks like a dome over our head. If you travel in any direction, you'll come to an ocean, especially here on the West Coast. But it looks like we're on an island. So the island surrounds our flat Earth ocean, or our flat Earth, with the dome over the top. Well, 2,000 years ago, that was the Hindu model of the Earth. With the and what's holding us up? Well, let's put it on the great beasts. So the Earth is being held up by elephants, and the elephants are standing on the back of a big sea turtle, and it is swimming in that endless sea. And the sky is a big snake holding onto his tail. Why not? That's what it looks like to our senses. And what astounds me is today we have the Flat Earth Society. There are people with this ridiculous model of how they think the world works, but they only believe what they can see. I have a question. I have a couple of questions about this model. One, why has there been no expedition to the edge to see what that dome is made of? It's supposed to be a big dome over top of us. And they say that the sun is up at the top. And the way we get day and night is that the sun shines like a spotlight. It only gives off light on one side and it rotates itself around like this. I'd like to know how they explain the physics of the dark side of the sun. But anyway, that's their model. And it astounds me in 2025, 26, we still have people who will believe this only what they see and not really accept science, not accept evidence, not accept the scientific way of thinking. It really disturbs me that we have, and it's not just the flat earth. We've got people denying climate change, people denying we landed on the moon, people denying all kinds of things. And it's really sad to me that there's so much disinformation and misinformation out there that people are believing rather than good science, but that's another issue. So we got out of that historically with this guy. Again, it was 1,200 years ago, I think, or 1,400 years ago. His name was Eratosthenes. If you know this story, just bear with me because I really like telling it. So Eratosthenes was a Greek mathematician, and the Greeks believed that the earth was round. Because, I mean, the moon is round, the sun is round, why shouldn't the earth be round? They just didn't know how big it was. And he was the first to measure the earth, and he did it with a stick. And I wrote a whole book about that called Measuring the Earth with a Stick. And it's very clever the way he did it. He worked at the Great Library of Alexandria in Egypt. He was a curator of that. And it was the greatest gathering of scientific knowledge back then in those times. And it was just thousands and thousands of scrolls from all of the civilizations before that had come along, not just the Greeks and the Romans, but Sumerians and all of that. So it was a tremendous library. Unfortunately, it got burned to the ground. But that's not where he lived. That wasn't his hometown. So you can see on my fabulous map of Egypt here, the library is at the top on the Mediterranean shore at the mouth of the Nile. You can see the Great Pyramids there. That's where the library was. But his hometown is Syene, which is up the Nile River. Now, he knew the distance between those two towns. He actually had a runner run it so that they knew exactly how far apart those two towns were. And the story goes that he was at home in Syene. We now call it Aswan. There's a big dam there. But the story goes he was at home and he went to the town square and there was a water well. And at high noon, he looked down the well and he saw the sun. And that meant that the sun was exactly overhead. It just happened to be June 21st, the summer solstice. So I don't think it was an accident. I think he was doing an experiment. And his thought was, if the earth is flat, since sunlight comes down in parallel lines, on June 24th, no matter where you are, you should be able to see the sun in a well. It would be straight over your head. So he waited a year. He went back to Alexandria. And what he's hoping is that if the earth is round, then you'd be over the curve when you go north. So you should see an angle here. Here's really what he's looking for. He's looking for this angle at the center of the earth. And he can do that by looking at shadows. So the following year, he goes back to Alexandria, but there was no water well to look down. So instead, he used a gnomon, which is the center part of a sundial, you know, the part that makes a shadow in a sundial. If you just take that by itself, it's called a gnomon. And there's a variation on that has a scale on the bottom so you can measure the angle that you're getting from the sun. So he puts this on the ground. By the way, they still do this today with students in Alexandria. They do the Eratosthenes experiment. I don't think Eratosthenes had water bottles though, but anyway, they're still doing it. So he waits. Now, if I could travel in time, he's one of the people I would like to meet. And I think it would be really neat to meet him as he's doing this experiment. So he puts this stick on the ground and then he waits for the sun to pass over at high noon. And he's watching the shadow get smaller and smaller and smaller. So I'd like to come up to him and say, excuse me, what are you doing? I'm measuring the earth. Really? With that, you're measuring the earth? Yeah. Okay. And then just wait. So he waits and the shadow gets smaller and smaller and smaller. If it disappears, the sun's straight up, the earth is flat. End of story. But of course it didn't. He got 7 degrees. That's as small as it got, 7 degrees. Okay, so that's the piece of the pie that he's looking at, because the Earth, a circle, is 360 degrees. So 7 into 360, 50. It's about 50. So he found that the distance between Syene and Alexandria is 1/50th of the distance around the world. And he just did that in his head. He just multiplied that distance by 50. And the number that he came up with was right on. Now imagine, this is his world. This is his world. That's all they knew at the time was the Mediterranean, a little bit of India, a little bit of Asia. That was it. They hadn't sailed around the world yet. The compass had not been invented. So for him to realize that the Earth was so much bigger than what they knew, I mean, it'd be interesting to just ask them, so how big is it? It's really big, man. It's really big. So his experiment showed that the knowledge at the time was so much less than what was out there, that the Earth is so much bigger than what they actually knew. And if I could travel back to him, imagine showing him this photograph, which is the last photograph of the whole Earth taken by human hands. This is from Apollo 17, the very last mission to the moon. Harrison Schmitt, the only scientist to go to the moon, took this. He was an avid photographer, and they were the only mission to have a whole Earth. And they got this, what's now become sort of the poster child for the environmental movement. But look what's in the picture. Africa. And up at the top is the Mediterranean. That's Alexandria. And just south of that, Syene. So I find it profound that the very last picture taken by a human hand of the whole Earth goes right back to where human hands measured that very planet. I find that very poetic that happened. Anyway, Eratosthenes would be astounded to see this picture. What? You got off the Earth? You saw it from space? Wow. It's quite an accomplishment, I think. So that was our first indication that we live on a big planet and our ignorance is greater than our knowledge. But there was a problem. They still thought that the Earth was at the center. And there's this problem of retrograde motion of the planets, especially Mars, because they wander among the stars. That's what the word planet means, wanderer. And they back up every now and then go ahead again. What's that all about? So there must be something else going on if we're at the center of the universe, which is what it looks like to our senses. It looks like we're in the middle. So Ptolemy comes along and he says, I have a solution. The solution, called epicycles and deferents. So there are little circles that the planets are on, and then the big circle that the rest of the stars are on, and they all interact with each other. And this is trying to solve mathematically the problem of retrograde motion. The difficulty is it got so complicated when you include all the other planets, it starts to break down. It was just getting so complex to try to account for the motions of all the planets. So this was wrong. This model was wrong. Enter Copernicus. Copernicus says, let's put the sun in the middle. Now it all makes sense. Now it's easier to explain. And there was, again, a tremendous revelation. We're not the center of the universe. We're not as important as we think we are. We're just a family, one of a member of planets going around our star. And then Galileo actually saw it. He saw orbital motion with his telescope when he pointed it at Jupiter, which I know you all do when you have clear nights. And Jupiter's up right now. It's in opposition. It's really big. But he saw the 4, what we now call the Galilean satellites, and he saw them night after night after night, and he saw them change positions, which we can still do now. And so he realized, hey, little things going around a big thing. So the little Earth must be going around the big sun. So this is empirical proof that orbits actually work. Orbits actually happen in nature. I can't wait to tell the Pope. Of course, the problem was in Galileo's time, the Pope was an amateur astronomer who believed in the Earth-centric model of the universe. So popes don't like to be told they're wrong. And so we all know what happened to Galileo. By the way, if you're ever in Florence, Galileo's house is still there. I've been in it. It's now a museum. So you can go into his home. You can go into his kitchen where he lived because he was under house arrest for the rest of his life. It's really quite a profound experience to sort of stand in the doorway and think, wow, Galileo stood here. This was his home. So now we're no longer at the center of the solar system. Terrific. Edwin Hubble comes along and he realizes that we're in a galaxy. Our Milky Way galaxy is what he called an island universe made up of millions. We now know hundreds of billions of stars. But beyond that, when he looked out at other galaxies, okay, so here we are, here's our home galaxy, and it's huge. It's huge. If you want to go from where we are to the center, 30,000 years at the speed of light. If you want to go to the other side, 100,000 years from one side to the other at the speed of light. We're nowhere near that. So that was a profound thing, that we're in this island universe. But then Hubble looked out and saw other island universes and saw that they're distinct from us. And not only that, they're all moving away from us. And the strangest thing that he saw was not only is the universe expanding, but the farther away something is, the faster it's moving. And that's not the way explosions work. If you think about fireworks, it goes boom, and everything starts from one spot, and it all races out at the same speed. The universe isn't doing that. As it expands, the ones closest to us are moving slower than the ones farther away. So how do you do that? What's going on? It's more than just an explosion. Well, Einstein came along and said, well, I got an answer to that. Space can stretch. Space is flexible. So it's not that so much that the galaxies are moving away from each other, it's that the space itself is stretching apart. It's stretching, and that's a hard concept to get around. And that gravity is not just a force, it's a curvature of space-time. So space and time are flexible. They can be, and that, again, this, I still have trouble with that whole idea of general relativity, but that was his big contribution to this. This guy, Fritz Zwicky, made another major discovery about the nature of the universe. He asked a simple question. He was looking at a cluster of galaxies. And the question that he asked, how much gravity does it take to hold these clusters together? Well, gravity is based on mass. So he added up all the mass of the galaxies in this cluster to come up with how much gravity would hold them. And there wasn't enough by a long shot. And this became known as the missing mass of the universe. Where is this? There's something there that's holding them together that we don't see. Vera Rubin came along later, and she did the same thing with just a single galaxy. She asked, okay, if it's rotating, what's holding the stars together? And when she added up the mass of all the stars in the galaxy, there is not enough gravity to hold the galaxy together. Those stars should be flinging apart like a lawn sprinkler. They should all be rushing off in all directions, but they're not. So there's something there we don't see, and we now call that dark matter. And it turns out that there's probably more dark matter that we don't see in a galaxy than the stars that we do see. It seems to make up about a quarter of all the matter in the universe, dark matter. And when scientists say dark, I laugh when I hear that. Dark means, I don't know. we don't know what it is. But there's a lot of work going on right now to try to find out. And one of the big experiments is right here in Canada. In Sudbury, Ontario, what used to be the Sudbury Neutrino Observatory, deep underground in a nickel mine, is now looking for dark matter. So it would be great. I mean, Canada won the Nobel Prize for figuring out neutrinos and detecting them. Maybe we'll win the Nobel Prize. Maybe Canada will be the ones to discover dark matter, what those particles or whatever they are actually made of. So that's active in Canada. Most Canadians don't realize that when it comes to astronomy, Canada's number 3 in the world. When it comes to scientific publications and citations, we're number 3 in the world. That's astounding. We're so quiet about it, you know. Anyway, so there's dark matter out there. And by the way, the Vera Rubin telescope, I'm sure you've been following this. It just opened just last year, and it's giving us tremendous views of the deep sky. It's a different kind of telescope. It's not the biggest, but it has the biggest camera. So it can do all sky photographs every night. And it's going to, for 10 years, it's going to take pictures of the whole southern sky, because it's in Chile. And then they're going to put them together into a movie of the universe, because everything moves. It's just at our human pace, we don't see much motion, excuse me, from one night to the night. But it's going to see the universe in motion. It's already seeing asteroids and planets and things like that. But it's going to see colliding galaxies, and it may even see the influence of dark matter as well. So it's kind of neat that the telescope in her name, since she was part of one of the pioneers for discovering dark matter. Oh, by the way, the rest of the universe is pushing it apart even faster and faster and faster, and that's dark energy. And we don't know what that is either. Those two things, dark matter and dark energy, make up 95% of the universe. We think we're so smart. We think we figured it all out. We don't know what 95% of the universe is made of. So our ignorance, like Eratosthenes, our ignorance is still far greater than our knowledge. Yes, we figured out a lot. We have figured out a lot, but there's still a lot we don't know. And I find that exciting. I find that really exciting. So here's where they think dark matter might be. Just these clouds that are bigger than entire galaxies. And the dark matter probably had a role in the early evolution of the universe, but we have to map it. We have to find it. We have to characterize it. And that's still some ongoing work. Then we have the James Webb Telescope that is not only seeing more clearly, but is seeing further back in time than we ever have. And it's shaking things up too. It's showing us that our standard model of the universe, how we think the universe began from something that was very hot and dense and then expanded out into what we know today, is not right. Because it's seeing galaxies that are 13 billion years old that are already well formed. And our model is that galaxies shouldn't form that quickly. First you get from gas to stars and stars to galaxies, and it takes time to do that. Well, Webb is saying our time is wrong. Our time scale is wrong on that. So it's called the Hubble tension between what we think the expansion of the universe is. So either we're wrong in time, the universe isn't expanding as quickly or as slowly as we think. We have to rethink the standard model. And here's another one that I find really fascinating to help explain that discrepancy. When we look at the universe on the largest of scales, all the galaxies that we know of, we see that they're distributed in filaments. There are these enormous cosmic scale strings of galaxies, is how they work. And there's a theory called the time scale, that maybe time doesn't run at the same speed everywhere. Because Einstein told us that if you're in a heavy gravitational field, time actually slows down. And if you're not in that field, time will run faster. So the idea is that maybe in the dark spaces between those galaxies, maybe time's running at a faster rate than it is in the denser parts. Interesting theory. And that would distort our perception of time and on the universal scale. So it's just something to think about. It's where we are right now in trying to understand our place in the cosmos. So over time, science has shown us that what we know is wrong, but thanks to science, we have figured out a lot. We've realized that, we weren't entirely wrong, but we keep modifying it as new instruments come along, as new thinkers come along, and it's exciting. And it's still ongoing today, where there's still a lot we don't know, including what's going to happen to the Earth in the next little while as we impose our technology on it. I want to leave you with one other thought. I love science fiction, Star Trek, Star Wars, all that stuff, all space. And it shows spaceships hopping around the galaxy, going from one star system to another, even at warp 10. I got a lesson in how slow our spaceships really are. I've lived it. I'm sorry, I missed the point. Here's one other thing we don't know. What went bang? What was it that went bang? And why did it go bang? We don't know. It was just incredibly dense, incredibly. Was there something before that was a big crunch? Are we actually living inside a black hole? That's an interesting thought. I'll just leave you with that. But in 1977, a spacecraft called Voyager took off from Florida. There were two of them, Voyager 1 and 2, and they were on a grand tour of the solar system, the outer solar system. They went by Jupiter and Saturn, And then Voyager 2 went on to Uranus and Neptune. It was a once in a lifetime opportunity because back then in the 70s, the four major planets were all on the same side of the sun. That only happens once every 174 years. So they took advantage of that. And each time they did, the gravity of the giant planets sped them up and gave them enough velocity that they could escape the sun. So now that they've done those missions, it took 12 years to do that. Voyager is now out between the stars. It's an interstellar mission, and we're still listening to them. We're still talking to them. The cameras are not on. There's nothing to see out there, but they're still out there. And they're about to approach 1 light day away from here. So when they want to talk to Voyager, it takes a signal at the speed of light, 24 hours to get to them. And then when Voyager answers, it's another 24 hours for the Voyager signal to come back. 1 light day. So the controllers have to wait 2 days to talk to it. So 1 light day, that doesn't sound very far compared to 1 light year, but it's taken almost 50 years for our fastest spacecraft to go 1 light day. Well, I was at the launch of Voyager in 1977. That's me on the left with all the hair. That's before I started dyeing it gray like I do now. Sitting beside me in the center is John Lomberg. He's a space artist who worked with Carl Sagan to put the golden record on the side of Voyager. John designed the cover of it and did some of the artwork on the digital images. So here's John and I at the launch of Voyager in 1977. Here we are at Uranus in 1989. 1989. Both of us had cleaned up our act a little bit. And no, in 1986 at Uranus. 1989 was Neptune. We kept going back to the Jet Propulsion Laboratory where they control the robots. And just over John's shoulder there on the left of the picture is the golden record. It's a model of it that's on the side of Voyager. Well, here's what John and I look like today. I saw him just recently. He now lives in Hawaii. Look at how different we look. We have aged. We have grown old and gray and wrinkled and a little bit shorter. The chief scientist, Ed Sohn, who worked on the program, is now dead. So are a lot of the other scientists who worked on it. It has taken the better part of a lifetime just to go 1 light day. If we want to go to the 1 light year, it's going to be something like 17,000 years at the speed of Voyager. 17,000 years to go 1 light year. And to go to Beta Centauri, our closest star, 4 light years away, is something like 70,000 years. It's nuts. It's nuts. Our spaceships are so slow, And even at warp 10, it's still going to be thousands of years to go anywhere. It's the universe is so large and we're so slow. And the big lesson in all of this is that this is it. This is it. This is all we have. This beautiful blue planet of ours, the only one we know of that's alive. They're up to what, 6,000 planets now that we see around other stars? None of them are like the Earth, none. Maybe there might be one out there, but if there is, it's going to be so far away we can't get to it. So this is it. This is our oasis. People will go to Mars, but it's going to be a hard life because there's no oxygen in the atmosphere, no ozone layer to protect you. They'll have to live underground. They'll have to wear spacesuits everywhere they go. It's going to be a hard, hard life. I don't believe Elon Musk's vision of 1 million people living on Mars. It's a cold, dry desert. It's a hard, hard place to live. We will go there, but very few people will do it. So this is it. So this is why we really need to take care of it. It's all we have. And we're learning about it. There's still a lot we don't know about Earth, but we're learning. And that's why we need science. We need science. And that's why I really value what you folks do in bringing the public out and showing them the universe through your telescopes. It's great. It's a wonderful public service that you're doing. Please don't stop. So I'm going to leave it there. And if you have any comments or questions, I'm happy to talk to you. But thanks again for having me tonight.
So if you have a question, it means you need to come up here and ask a question. We've tried to repeat questions, but then people go on for 4 paragraphs. So that doesn't work. So if you have a question, please come up here. And then we'll pause, and maybe there will be somebody Zooming who wants to ask a question. But for now, we'll just keep it to the live audience. So, is there anyone who has a question that they would like to ask? Oh, come on.
He's just done too good a job. I'm going to start. Take it away.
Okay, so you mentioned timescaping, where the time runs differently in different areas where the mass is different. Where are we with that? Because one of the things that they are claiming with that theory is that that means there's no dark energy at all.
Yeah, well, because we're in a galaxy cluster, time is running a little faster for us. So that might seem like the universe is expanding faster than it really is. So depends on where you live, but you'd have to go a long way away to get to one of those empty spaces. I'm not quite sure the distance, but it's millions of light years away from here.
Do they think that the Vera Rubin movie that you were mentioning is going to make it possible to see whether that expansion rate is different in different areas?
Yes, that's the whole purpose of it. It's a 10-year project. So we should see enough motion in 10 years to detect that. That's what's remarkable, because all other telescopes take single shots, right? So Rubin is going to make a movie of the universe. We've never had that. That's going to be astounding to see what it finds. And I'm looking forward to the surprises, to see things moving in ways we didn't expect.
Anybody else? I'll keep going. One of the things I've been following on sites like Astrobin is teams of amateurs and professionals who are spending hundreds of hours and then combining all of their images to find really faint supernova remnants and integrated flux nebulas and things like that. We're discovering all kinds of things that our ancestors or astronomers missed. There's all kinds of stuff out there that is relatively close that we haven't found yet.
Absolutely. And that's the value of what you do. You're out there just saying, hey, what's up tonight? You're looking at the whole sky and saying, oh, look, there's something I didn't see before. Ian Shelton from University of Toronto, he discovered a supernova by just walking outside. He was down in Chile at an observatory and he took a break and he just went outside and looked up. And because he knew the sky, he saw a new star. And so he reported it, and now we have 1987A. And since then, we've been able to watch that progress because he caught it right at the very beginning. Astronomers, professional astronomers, they already know what they want to find, and the telescopes have such narrow fields of view that they're just looking at one thing, and they're trying to prove what they already know, basically. I mean, the Hubble, the deep field pictures that we're getting from Hubble and from Webb, the amount of sky that they cover is the equivalent of looking through a drinking straw at arm's length. It's just a tiny, tiny little bit. And yet they're seeing hundreds of galaxies in this little bit of sky. So your work, just going out and seeing what's there and seeing what's new, yeah, that's really valuable. And astronomers need that. That's why we need, everybody just appreciating the night sky.
Do we have any questions online?
I do.
Oh, right behind you. You got one? Go for it.
The James Webb Telescope, how close to the Big Bang has it got?
They're almost back to the beginning. It's not just Webb itself that's looking back 13.5 billion years. The universe is, 13.8 billion? But thanks to gravitational lensing, where you'll have a cluster of galaxies and the gravity causes the light to bend and magnify an object that's further away, they're starting to see. That's how Webb, with its higher resolution, can see objects further back. So they're almost back to cosmic dawn. We just did an item, it'll be on tomorrow on Quirks, about a monster black hole that they've just found way back at I think 13.5. And and they were surprised that it's so far back in time. It's a giant black hole, but there are no stars around it. It's a galaxy without stars. But they can't go back too much further than that, because you get to a point where all you're going to see is gas. And then the universe went kind of opaque. You couldn't see through it. And that's the cosmic microwave background radiation, which is the farthest back we've seen. But what Webb is doing is seeing the early evolution of galaxies and stars and black holes, and hopefully dark matter.
Projects like Galaxy Zoo, where they're
inviting people to help scientists find things up in the sky. You've got a whole thing called Zooniverse now where people can sign up to help people find supernova remnants and track things through the sky. What can you tell us about that?
Well, there have been a lot of these citizen science projects around for a while. I know the SETI, Search for Extraterrestrial Intelligence, had a program that you could download and it would run in the background on your laptop or on your computer and help them look at data, because they're dealing with such large amounts of data in radio emissions that you could help filter that down. And I think I don't know of specific ones that are happening like that now, but it's a common thing to sort of network people who would join in to handle large data. Although now we're getting artificial intelligence to do that, because these smart systems now can see patterns that people don't. But I think we'll always have room for citizen science. Absolutely.
I agree. Oh, okay, now I'm going to dare the people who are on Zoom to ask a question. Now, I'm a bit afraid, because what that means is you have to unmute yourself and then ask the question. If there are two people unmuted at the same time, one of you's going to have to turn off. And if you leave it on, then we're going to find out that somebody's having a bath upstairs. Okay, so do you understand? Okay, so is there anyone on Zoom who would like to unmute themselves and ask a question?
It's a question about the cosmic microwave background radiation.
Yes.
How come we can still see it? I mean, for example, when there's a supernova, you get to see it, but if you miss it, it's gone, right?
Microwave background is just a very faint glow that comes from all parts of the sky, and it's showing the density variations in the primordial cloud that we came out of, showing that it's more or less uniform, but there are fluctuations in it that are very very slight, and it's believed that those density differences are what eventually coalesced into stars and galaxies and us. That if they weren't there, that we wouldn't be here. If the universe was uniform in all directions, it would have been just an expanding gas. So it's kind of beyond the stars. It's a microwave radiation that's coming from the sky itself. It's not coming from individual objects. That's why we can see it.
But if it happened in the past, how come we can still see it?
Well, that information is just getting to us now. It's taken 13.6 billion years to get here, so we're just seeing it. The whole universe is like that. Everything from the past, that information takes time to cross the universe, so it's just getting to us now. The Big Bang happened a long time ago. We're seeing the past. Telescopes are time machines. When we look out, it's one of the advantages and disadvantages of telescopes. We have two choices. We can either look back in time, but then you come to a limit. You can't look any further back than the beginning. So we're in this sort of sphere, a perceptual sphere that we can't see beyond because we're limited by time. If we could see the whole universe at once, if that wasn't there, we'd be able to see how big it really is. We'd be able to see the edge of it, if there is an edge. So we can't. So that's the problem. And no matter where you are, everyone is in their own little sphere of perception of the universe. That's just the way it is, as far as we know now.
Okay, thank you.
Okay.
What do you anticipate will be the most exciting discovery that Webb will make?
Webb. Well, Webb is it's on a multitask mission. Part of it is to look out to the edge of the universe and see the evolution of galaxies, but it's also looking at planets going around other stars, and it can do chemistry of those planets. And there's a Canadian team that's on doing that. And I find that kind of exciting because planets are turning out to be so bizarre. A lot of them are really close to their stars. Some of them have atmospheres that are so hot, the atmospheres are made of metal. We've got planets that are locked to their stars. So one side's going to be super hot, the other side's going to be super cold. So you got the Sahara Desert on one side and you have Antarctica on the other. What kind of weather are you going to get on these planets? So I'm kind of looking forward to that. I'm more of a planet guy than I am because of my Voyager experience. And I could do a whole other presentation on what that was like to be there at the Jet Propulsion Laboratory when we went to places for the very first time and saw things that human eyes had never seen before, especially the moons of Jupiter. Io with its volcanoes coming off out of an orange moon with volcanoes. Wow, nobody expected that. Europa with its ice. Further out, we got there's one called there's Iapetus, which is two-colored, one on either side. Anyway, it was just a delight. And then to go to Pluto with New Horizons, I went to that there as well, to be there when we saw Pluto for the very first time. And we saw glaciers made of nitrogen ice. Nitrogen ice. The air that we're breathing right now on Pluto turns to ice. And you can't ski on it, and you can't make a snowball out of it, because it turns out that nitrogen ice, while it looks like regular snow, if you hold it in your hand, it'll be like yogurt. It would flow through your fingers. Wow, that's real. That's really there. And that nitrogen ice, those glaciers, are flowing between mountain peaks that are made of water ice. Water ice that are mountains that are as high as our Rockies. Wow. Can you imagine seeing that? Seeing Mount Rundle from Banff made of water, a crystal? Wow. So I'm really excited about what Webb might find in terms of other worlds out there that are so alien and so very, very different from us. And hopefully the Holy Grail, finding another Earth-like planet. But even if they do that, it won't be like the Earth. It'll be a variation on Earth. And who knows, maybe somebody to talk to. Yes, sir.
Thanks for doing this, Mr. MacDonald. I'm interested in what the Japanese are doing with their lunar rover, and what do you think they're going to develop that'll be new for us?
Yeah, the Japanese have done a lot with their rovers on the moon, but I'm more interested in the Chinese because their program is really advanced. They've got their own space station. They have their own taikonauts. They have landed rovers on the far side of the moon, which has never been done before. They did a sample return mission from the moon, and they're planning to send humans to the moon. And I wouldn't be surprised if the next flag to be planted on the moon is red, because they're very progressive. They're just going stage by stage by stage, and they're not slowing down. Whereas the U.S. program has been delayed. That SLS rocket that's going to carry Jeremy Hansen to the moon later this year, it cost $4 billion to fly it, and it hasn't flown since 2022. It's crazy. And they want Elon Musk's Starship to be the lander. Well, it hasn't even made it around the Earth yet, let alone land on the moon. So it's going to be they're saying they're going to do, the Americans are going to land on the moon before 2030. I'll be amazed if that actually happens. But the Chinese, you watch out. You watch out. They're doing a lot. So it's going to be interesting to see who's the first to get back there.
When you were younger, did you ever have the chance to see any of the science fiction movies that Ray Harryhausen illustrated? I would imagine those influenced you.
My very first science fiction movie that I saw was The Day the Earth Stood Still with Michael Rennie, the original one. And I think it still holds up today. It's just a fabulous, fabulous film. It's so straightforward. And of course, I saw the opening of 2001: A Space Odyssey, and all the B movies as well. It Came from Outer Space, and all of that stuff. I love them. They were just fabulous. And we need that. We need that imagination to stretch ourselves out. And I actually had a funny situation during Voyager at Saturn. When we got a close-up image of its rings, they found that the outer F ring had kinks in it. It wasn't nice and symmetrical. It had waves in it, and it was the Enki. We call it the kinky Enki. And so they weren't quite sure at that time what was causing that. Now we know there are little moons in there that are going around that are shepherding them. But while that picture came in and we were just in the press room, there was a guy sitting beside me. And I thought, oh, I'll just get some ambience. So I took out my tape recorder and I said, do you want to just tell me who you are? And he said, oh, my name's Larry Niven, famous science fiction writer. And I said, oh, so are you getting inspired by this? And he says, oh, you bet. And not long after that, Larry Niven came out with a novel, and I'm struggling with the name of it, but the opening scene is a spacecraft embedded within the rings of Saturn by these aliens that are hiding there so that we won't see them. And one of them started the engine and it caused a disturbance in the rings. And the other one said, oh no, you're giving us away. You're giving us, they're going to see us. So I love science fiction. I love science fiction. It's great.
Thank you.
Okay, I've got to interrupt the Zoomers now and back to the live audience. So go ahead.
So how do I get a ticket on a 0G flight, and can I do it on points?
No, it's fairly expensive. It's like $3,000 or $4,000, I think, per ticket. But you know what was funny on that is that the people that were on it were all like us. They were, people spending their retirement or birthday presents, Christmas presents, and a lot of them were, people who grew up in the space age. Like I can tell you all dye your hair gray like I do. So you saw the moon landings, right? And we were all inspired by that. So that's the majority of people that were on that flight. I was quite surprised.
So how do I actually buy a ticket? Like who's running that?
You can look it up online. It's called Zero G Inc. And they fly out of Fort Lauderdale, Florida. I think they also fly out of Las Vegas. They have a couple of them that they do. And it's a 737 jet. It's a half-day experience. You start out in the morning in a hotel where they feed you. It's good to have something in your stomach, not a lot. And they show you a training video to tell you what not to do. So they show you other flights that people go on. And the first thing they say is, don't swim in the air. Because your first tendency when you go weightless, when you lift off the floor, is to flail your arms around and do this. They said, it doesn't work. You can't swim in the air. All you're going to do is kick somebody in the head. So that's the first thing they tell you. And then they tell us about that feet down thing. Because when they pull the plane up out of the dive, you go through 2 Gs. And so you could be in any position. So you got to get your feet under you, then you float down to the floor and then pull up. So those are the instructions you get. And then the flight itself is about, it's a little over an hour. We did 15 parabolas. And they do them in sets of 5. They have a piece of air out over the Atlantic that's 100 nautical miles long and 10,000 feet thick. I think it's between 20 and 30,000 feet. It's quite high. So they can only do 5, and then they have to turn around and then do 5 again on the way back. And it's during that turnaround period where you're back to 1G that you can try to plan what you're going to do next. And that's how I plan to be spun around by that guy. We also did some other things that you didn't see in the video that kind of worked, sort of worked. But what was odd for me is I had a cameraman with me. And we had planned all kinds of things I was going to say to camera. Soon as we went to 0G, I was floating, he was floating. We were all over each other like this. So I could only get out a few things at a time. So we made all that up on the spot as we were going along. But it's an amazing experience. If you can save your pennies, go for it.
Thanks.
So somebody on Zoom asks, why did they make you wear a USA flag when you were on the Vomit Comet?
They give you a suit. They give you a one-piece flight suit that you get to keep, actually. And so I still have it. But nobody got sick. You also take some medication beforehand. They have you get it's sort of like a prescription Gravol. You have to get a prescription for it. But it's like a super Gravol. So you take that with your food, and it really settles your stomach. But nobody got sick. Again, because you can't see out, you don't get that conflict between your eyes and your organs of balance. That's what makes you sick. If you're on a ship and you're down below and you can't see the horizon, or on a boat and it's moving, you're getting a conflict between what you're feeling. Your ears are telling you you're moving, but your eyes see that something is still. And they believe that that's a poison response, because when you take a poison, or if you get yourself really hammered, you drink a lot, you stagger, right? It affects your organs of balance. So they think that it's your body thinking that you've been poisoned, so that's why you want to throw up. So they give you meditation. But when you don't have that conflict between your eyes and your ears, you're just feeling it. There's no problem. It's just weird, and it's great. It's a lot of fun. Mike, if you can, yeah. And
AI and
yes,
its use on researching exoplanets. And the second question is, how much are we missing in terms of exoplanets that we can't see, in the sense that an exoplanet has a transit across its sun?
well, I think it's generally believed that just about every star has planets. So that makes, well, just in our galaxy, more than a trillion planets just in our galaxy alone. So, you know, that's a lot. And you're right. We're only seeing the ones that are either doing the transit method or the wobble method. You can use that too, which is harder, but you can do it. So I think there's a lot we're missing. We're just seeing the tip of the iceberg, and that's exciting. You know, that's exciting. But the fact that probably every star in our galaxy, including red dwarfs and unusual stars, have 3 or 4 planets around them, maybe more. So the odds of finding planets are pretty good.
Hello, my
Hi.
name is MacDonald, and I had the pleasure of meeting you when I was at the national conference back in Victoria a few years ago. And again, when you came and spoke to the RESC in Vancouver. And I want to say it was always a pleasure and inspiring to hear you and your great adventures. And I really enjoyed the way that you can speak to us in a way that we can all understand. And thank you so much for taking the time to come and speak to us here.
Well, thank you so much for that. You're very kind. I'm sorry I can't be there in person, or couldn't be there in person. I just missed you when I was there last time giving a talk about my latest book. However, I am going to be in Gibson's next September, talking about my latest book, Just Say Yes, which is my autobiography. And so look for that. It's September 15th, I think. It's a Sunday. So I'll be there if you'd like to meet me in person. But thank you very much. You're very, very kind.
Well, yes, and so that was a good a thank you conclusion, even though that was not official. But, so we do thank you, Bob, for tuning in to our meeting today, and we appreciate your engaging with us and telling your exciting stories and adventures. So thank you very much.
Okay, is it possible to turn the camera around so I can see the audience?
You bet.
Oh, there you are.
There we go.
Hi, everyone. Thank you so much for coming out tonight. Glad to see you're all here. Clear skies.